Okay, in this video, I would like to discuss the chain rule for finding the derivative of a composition of functions. So we already know how to find the derivative of things like cosine x, x squared plus 9, and e to the x. But what we don't know yet is how to find, well, let me just use two colors here, something like cosine of x squared, or x squared plus 9 to the fourth power, or e to the x cubed. All right. So what we're finding here actually is cosine. This is a composition of functions. We're doing cosine of x squared as opposed to just cosine of x. Or we're taking x squared plus 9 and we're raising it to the fourth power. Or instead of raising e to the x, we're raising e to the x cubed. All right. So we have kind of an inside and an outside function here, and so they're all of the form f of g of x, where you have an inside and an outside function. So very briefly, let's discuss what would be our inside and our outside function here. So if we look at this as f of g of x, one way to do this is that if you just say it, you hear the of, cosine of x squared. So the f of x is cosine x, and g of x is x squared. So when I say f of g of x, I'm replacing x here with g of x, which is x squared. Here, it's x squared plus 9 to the fourth, right? So this is the inside function being raised to the fourth power. So my f of x would be x to the fourth, and my g of x, the inside, is x squared plus 9, right? Because if I do f of g of x, I'm putting an x squared plus 9 in here for x, so that whole thing gets raised to the fourth power. Here, e to the x cubed, so notice that this is being put in for x here, right? Instead of raising it to the x, we're raising it to the x cubed. So e to the x, g of x is x cubed, all right? So f of g of x would mean we put g of x in here for x, so the x cubed replaces the x, and we get e to the x cubed. So just in terms of, I just want to in order to kind of maybe give you some intuition about how the chain rule works, what it's basically, let me state it first. The derivative of a composition is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Many times you may also see this written as, so we have this f of x equals f of g of x, and we'll let u equal g of x. All right. So now we have this f of u is, well, this is actually still f of x. Here's my f of u, right? Because I've replaced g of x with u. All right. So many times, this is one notation that you'll see right here. Here's another notation where f prime, or you can think of it as df dx, equals df du times du dx. All right, we take the derivative of f with respect to u times the derivative of u with respect to x. But notice that's the same thing as what's going on here. We're taking the derivative of f and we're evaluating it at g of x, which is u in this notation, times g prime, which is du dx, right, if u equals g of x. So just in terms of how to understand how this and this could actually represent the same thing, we're just doing this little substitution here so that we can kind of write it in terms of a multiplication. And this is a multiplication as well. So whichever notation makes more sense to you, either of these will get you there. In order to, again, develop a little bit of intuition about, it especially works with this notation. Suppose we had a race car race, all right? So it's a car race, and distance that the car has traveled is, so this is the distance function, and it is a function of time. So as a function of time. All right, and then we have the tread on the tires. The height of the tread is a function of the distance that's traveled. Oops, height of the tread, and it is a function of distance, right? How much tread these race car tires have left on them depends on what kind of distance has been put on them. I mean, it's true for all tires, but the tread on race car tires wears out more quickly because they're going faster and they're hotter. So if we wanted to find how the height changes as a function of time, right? So here, height is a function of distance, and distance is a function of time. But if I wanted to know how height changes with respect to time, then I could find out how distance, the derivative of the distance with respect to time, times the rate of change of height with respect to distance. All right? So again, you can kind of think of this as a composition of functions, right? Because the height is a function of distance and distance is a function of time. All right? So if we wanted to kind of skip over that and go right to what is the change in height with respect to time, we could find the change, and these are all derivatives. If I wanted to find the derivative, the rate of change of height with respect to distance, it would be the rate of change of distance with respect to time times the rate of change of height with respect to distance. And that's where this notation maybe makes a little bit more sense from that point of view. But either of these, you could use either of these formulas for the chain rule. So what I would like to do for the remainder of this lecture is just give an example of how to use the chain rule. And let's go ahead and look at these three functions, how we would use the chain rule to find the derivative of these. Okay, so let's start with the first one, which is cosine of x squared. All right, so we've already said that the outside function is cosine x, and that the inside function is x squared. So again, if we use, I'll do each of them. I'll do this example in both with no notations. But if we start off with f of x equals, or f prime equals, big F prime equals f prime of g of x times g prime, then what I need to do is find f prime of g of x and g prime, and then multiply them together. That will give me my answer. All right. So f prime is negative sine. Right? We should all know that by now. So f prime of g of x is negative sine of g of x, which is x squared. All right. So that's the first part here. My f prime of g of x is negative sine of x squared, and then g is x squared, so g prime of x is 2x. All right. So the derivative with respect to x of cosine of x squared is their product. We write it this way, but many times we'll put the 2x in front of the sign. So I would end up with negative 2x sine of x squared. This is just kind of convention that the non-trig function would go first and then the trig function would afterwards. But you don't have to do that. The point, though, is that it's their product of these two is the derivative of this. All right. We also could have let u equal x squared, so that f of u equals cosine u. Now if we use this notation, df dx equals df du times du dx. Well, that looks more like an O. All right, so df du, that's negative sine u, and then du dx is just 2x. And of course, we would have to replace u with what it actually equals to get our final answer. Alright, so again, you could write it this way if you wanted to, or this way. Either way is fine. It's just more often, especially if you're checking answers in the back of your book, that's what it will look like. Okay, so there's an example of how to use the chain rule for composition of functions. Let's look at the other two examples that we looked at the beginning of this lecture. So we had x squared plus 9 to the fourth. All right. We said that the outside function was x to the fourth, and that the inside function was x squared plus 9. All right. So again, if we're using this notation, that the derivative of the composition is the derivative of the outside function evaluated the inside function times the derivative of the inside function, then you find f prime equals 4x cubed. And f prime of g of x, we're going to take our g of x and put it in here for x. So that's going to be 4 times x squared plus 9 cubed. All right, so we've got that piece of it. Now we need g prime, but g prime is pretty simple to compute at this point. It's just going to be 2x. Derivative of x squared is 2x. Derivative of 9 is 0. All right, so then the derivative with respect to x of x squared plus 9 to the fourth is this times this. If I simplify, 4 times 2x, that's 8x. X squared times x squared plus 9 cubed. All right, I want to point out here that we can generalize this idea. Notice that this looks a lot like just the power rule, right? Because we use the power rule here to get the derivative of x to the fourth, and we just kind of left this piece, we put g of x back in, but otherwise it's just the power rule. So we have this idea, call it the generalized, I can spell it, generalized power rule. All right, so we can find the derivative of some function to the nth power, and it would be the power times the function raised to the n minus first power times g prime of x. Notice that's exactly what we got here. Right, this g of x that's inside was x squared plus 9. We took the derivative by multiplying by the 4 and reducing it to a 3, and then we multiplied by the derivative of the inside. All right, so this can be useful. I mean, you can use this formula for its general formula for the chain rule, or you can use this more specific, which is the generalized power rule. Notice that actually the power rule that we have, so if I want to just take the derivative of x to the fifth, well, we know that's just 5x to the fourth. But notice that here you can think of this as a composition of functions where the inside function is just x. All right, and I'm taking x and I'm raising it to the fifth power. So I would have 5, using the generalized power rule here, I would have 5, my inside function is x, to the fourth, and then I would multiply by the derivative of the inside function, which is, inside function is x, so its derivative is just 1. So that gives us 5x to the fourth. So really the power rule that we already know is just a specific case of the generalized power rule, with the inside function being x instead of something more complicated like x squared plus 9. Okay, finally the last example. I like to switch colors, these pens get a little tired after a while. We were looking at the derivative of e to the x cubed. All right, so I'll use the other notation this time. We'll say that u equals x cubed, so that f of u is just e to the u. And our chain rule formula using this notation is df dx equals, actually this should be big F, right? Equals df du times du dx. All right, so first let's get df du. Well, here is f, so the derivative of f with respect to u is just e to the u, right? Derivative of e to the x is e to the x. If I have e to the u, then it's just e to the u. All right, so there's df du, and then du dx, taking the derivative of u with respect to x, is just 3x squared. All right, so I need to rewrite this now. My df, big F, with respect to x is e to the u times 3x squared. But I want this all in terms of x, so I need to replace u with what it equals. So I'm left with e to the x cubed times 3x squared. And again, the convention is usually whatever this is comes out front, just the way we write it. It's exactly the same. I just want to point out that the convention is the e to whatever goes on the back, and its derivative is in front. So this would be the derivative of e to the x cubed. We can also generalize this. All right, so if I wanted to take the derivative with respect to x of e to some function, all right, so instead of just e to the x, I have e to some function of x, in this case x cubed. It could be e to the sine x, it could be e to, I don't know, 3x squared plus 5. It could be anything, any function. So let's just derive this using the chain rule. So I'm going to let u equal my f of x. Just like I let u equal x cubed here, I'm going to let u equal whatever that is up in the exponent. So using this formula here, I'm going to get that df dx is going to be, again, df du times du dx. Well, df du, we actually already did that up here, right? That's just e to the u times du dx. That's just going to be f prime. Again, we usually put the e on the back, and I'm going to replace u with what is equal, which is f, so I just end up with f prime of x times e to the f of x. So the e to the f of x will always be there when we take the derivative of e to some function. It's just that we're going to multiply by whatever the derivative of that exponent is. So you can see that's exactly what we did here. We ended up with this e to the x cubed again. It's just that we multiplied by the derivative of x cubed. So this is a nice, simple formula for taking the derivative of e to some function. And I also want to point out that this formula right here is a special case of what we already know, which is that the derivative of e to the x is e to the x, right? Because in this case, our little f would just be x, and so when we multiply by the derivative of x, we're just multiplying by 1, we get back e to the x, so 1 times e to the x is e to the x. So really this general rule, or this specific rule right here that we already know, is a general case of this rule, which is ultimately related back to the chain rule. So that is the chain rule, and there are some examples of how to apply it, and some useful general rules in terms of the generalized power rule and how to take the derivative of e to some function of x.